we will have the third lecture by Konstantin Zarembo, but before that, let me remind you once again, tomorrow there might be a strike. We don't know yet. They're voting tonight. Please watch carefully the website for information. And what else? Oh yeah, so tomorrow there's the last poster session. So since we put the poster session at the very end, you know, you can put the posters up in the morning so that people can have the whole day to watch them. All right, so who are the people who are on the third poster session? Okay, so now let's start with a third lecture by Konstantin Zarembo.
Yes. The strike is for for public transportation, not physics professor. So I will still lecture tomorrow, so don't worry. Yes, I was talking about solving the Heisenberg model. So we were the task was to diagonalize this Hamiltonian. And the answer to that is written in terms of the beta equations, which take as input the dispersion relation for magnons in their two-body scattering. So let me first rewrite them in a nice algebraic form by changing variables. So we introduce the variable that's called rapidity, and it is defined in such a way that momentum is parameterized like that, right? So it's one way to write a pure phase is as a ratio of some complex number to its complex conjugate. So this is how we define U as a function of P. It can be inverted, of course, and then U is 1/2 of the cotangents P over 2. And this is precisely what, so this same cotangents arises in the scattering matrix, so that's why this rapid deparameterization makes equations simpler. So the beta equations then can be written as algebraic relations for the rapidities of magnons. So this is how the beta ansatz equations are usually written down. And these are algebraic equations. So there are n equations for n unknowns. And then once these equations are solved, the energy, or in this case, the anomalous dimension, can be computed simply by summing over rapidities, of the energies of individual magnons. So in the rapidity variables, the energy is given by this formula. So these are the beta ansatz equations. Let me give maybe just one example of solutions of these equations. So first of all, beta ansatz equations, they cannot be solved. They cannot be further simplified. So you need to solve these equations to find the spectrum. But it's still much, much simpler than just diagonalizing this Hamiltonian. So the Hamiltonian for spin chain of length L is a matrix of size 2 to the L times 2 to the L. So the complexity grows exponentially. You can diagonalize it on a computer for lengths maybe up to 10, 12. Whereas the beta equations are algebraic and their number grows linearly with L. So you can easily solve them up to, also the number of equations is dictated by the number of magnons. So I think that they can be easily solve up to 100 magnons or so. It's depends on what you want. If you want all solutions, then probably less. But individual solutions can be found for states that contain many, many magnons. They're also very useful in understanding some thermodynamic limit where you have, say, finite density state or antiferromagnetic vacuum, which is the state that has largest energy. So if you change the sign of the Hamiltonian, this would be the ground state of the spin chain. So they're definitely simplify the problem a lot. So let me give an example how to solve them. So we can find, for instance, the spectrum of all 2 magnon states for the spin chain of arbitrary length. So the magnons we'll consider will have opposite momenta. And if we want to apply this to operators in the superrank-Mills, then the total momentum has to be 0 because we are interested in states that are cyclically symmetric. So cyclic symmetry is the same as the condition of 0 momentum. Okay, so we just substitute this into the beta equations. So what we get is one equation for one variable. And you see that effectively what happens is that scattering of magnons cancels 1 power of L here. So the rapidities are the same as the rapidity of a free magnon, but on the spin chain of length L minus 1. So in a sense, interactions effectively eat up one side of the spin chain. So then the solution can be written simply because, well, from this formula, but with momentum quantized as if it lives on the spin chain of length L minus 1. So the solution is this. It's 1/2 cotangens pi n divided by L minus 1. And the energy or the anomalous dimension is lambda over pi squared sine squared pi p over L minus 1. So in particular, the simplest case is length 4. And this is because, so this number n is restricted to be in the interval from 0 to L minus 1 over 2. Otherwise, it will be a trivial solution. So the first case where any non-trivial solution arises is L equals 4, and then there is only one solution, and can be equal to 1. If you set L to the 4 and L to 1, then this angle is pi divided by 3. So the scaling dimension is simply 3 lambda over 4 pi squared. Right? The sine of pi over 3 is square root 3 divided by 2. So what we get is again the same number as the anomalous dimension of Kanishi. Yes? Here? Yeah. It's pi p. Okay. So we're just expressing. Well, I'm sorry. This is n. Yes. Thank you. All right. So we got the same answer as for Kanishi. Yes.
Corresponding the super Yang-Mills.
Just coming to that.
Okay.
So then we have length 4, so it's an operator with 4 fields. And this means that, so the state is with two spins up and 2 spins down. So spin up is field that we denoted by Z, and the spin down by W. So the operator that corresponds to this state is trace Z squared, W squared, plus permutations. So if you then look more carefully, and this can be done without calculations, then the wave function is such that it's that this operator is trace commutator squared. You can, after looking carefully, you can recognize that there are only 2 operators of this type. One of them must have 0 energy, and the only non-trivial choice is the commutator. So this operator has anomalous dimension, which is the same as the anomalous dimension of Kanishi, and that's again not a coincidence. So this operator can be written as some combination of supercharges acting on Kanishi will produce this operator. So I write this a bit symbolically. So supercharge has certain indices. You need to contract them in a particular way. And then you get precisely this operator with the right quantum numbers. So supercharge. So one thing that is easy to check is the dimensions work out. So Kanishi has dimension 2. And each supercharge has dimension 1/2. So indeed, you add 2 units of dimension and get operator of dimension 4. So in other words, this is a superpartner of Kanishi, and by supersymmetry, they should have the same anomalous dimension. All right. So then, in principle, you can compute anomalous dimension of any operator that made out of Z's and W's. But we are interested in a bigger set of operators. And in fact, we started with any scalar operator. So the next task is to solve the spin chain in the SO6 sector, so that for all operators containing arbitrary combination of scalars. So to do that, so in principle, we need to repeat the same story as here. We need to consider magnets of this spin chain, collide them together, find the S matrix, and then write down the beta equations. But it's not as simple as it sounds, because so there are more fields. So the magnon of SO6 spin chain will carry flavor, right? So there are 6 states. The ground state is still the same, trace Z to the L operator, but you can change Z to any of other fields. So it seems that there are 5 types of magnons. In fact, the right answer is 4 types, but that might not be immediately clear. Anyway, so the S matrix will be not really a phase, but it will be really a matrix by size 4 by 4. Before writing down the beta equations, one would need to diagonalize this matrix. So it's a rather long story. I want to somehow take a shortcut and write down the answer from, well, from, again, consistency, just to reconstruct it from symmetries. So for that, I will need a little bit of group theory. So I need to remind you some facts from representation theory of Lie algebras. So any Lie algebra can be written, its generators can be, for representation theory purposes, there is a very convenient way to write commutation relations in what is known as Chevalier basis. So one defines, one splits the generators in Cartan generators. Oh, I think this part of the Blackboard doesn't really work, so let me write it here. And positive and negative simple roots. So all other generators, so these are not the full basis of the Lie algebra, but all other generators can be obtained by repetitive commutations of these basic building blocks. So the important part is the commutation relations between them. So Cartan generators commute among themselves, and they commute with positive or negative roots. So positive and negative roots are eigen states of the adjoint action of the Cartan generator. So they produce, again, a linear combination of, let me see, it's not a linear combination, it's just, there is no summation over beta here. So they simply produce the same root, but with some numerical coefficient, and positive and negative root differ by sign. So this set of numbers, A alpha beta, is known as Cartan matrix. Then if you commute positive root with the negative root with the same index, you get the Cartan generator. And finally, there is some condition that's known as SAIFR relation, which I don't remember, of course, by heart, which tells you that upon applying positive or negative root certain number of times, to the positive or negative root of other type, you'll get 0. For alpha, not equal beta. And the elements of the Cartan matrix are integers. So these are basic, yes? For alpha not equal beta. The exponent, it's 1 minus alpha. 1 minus the Cartan matrix, A alpha beta. Let me write it again. So it means that if you commute E alpha with the beta sufficiently large number of times, you should get 0. So it cannot be repeated infinitely many times, yes?
I'm a bit confused about like the commutation relation between E alpha plus and E alpha minus, because like, does that mean that there's a Cartan generator corresponding to that positive simple root? Like all the indices are alpha.
All the indices are alpha, yes.
Okay.
Yes, there is a, yes. So it's basically any Lie algebra is a collection of SU2s in a sense. So for SU2, this would be sigma plus, sigma minus. They commute on sigma 3. And there are eigenvalues of sigma 3 when you commute them. So this equation tells you what happens when you commute the same positive root with the negative root. And this tells you what happens if you commute positive with positive or negative with negative. Yeah.
No, I was just confused about, so there are like, the number of Cartan generators is always exactly the number of positive simple roots?
Yes. So, and this number is called the rank of the algebra. So alpha runs from 1 to rank of G. Maybe I should give an example of this, and probably the best example would be SO6 itself. Before that, let me say about representations. So any representation, in any representation we can diagonalize Cartan generators because they commute among themselves. So each state then can be labeled by the eigenvalues of the Cartan elements. These are called Dynkin labels of the state. But among the states, one can also choose the state that's annihilated by all E plus generators, and this is called the highest weight of the representation. So we impose the condition that all highest weight, all E pluses annihilate this state. Then the Cartan elements acting on the state would produce some numbers. Which in that case are Dynkin labels of the representation. And the claim is that these numbers are always integers, like and actually they are positive. They are positive, non-negative integers, like the Cartan matrix elements. So all other states can be generated by repeated application of lowering operators. So the representation will be then spanned by vectors of this form. And each time we apply an lowering operator, the weight of the representation is lowered, so that the weight of this state will be equal to the highest weight minus the sum of rows of the Cartan matrix. Yes. There can be both.
Okay.
So they are, they need to be integers, but they can be either positive or negative.
And the exponent, what happens if the exponent is negative?
The exponent is negative, then, well, the off-diagonal components of the Cartan matrix, I guess, are always negative. So the exponent is positive.
Always.
Yes?
So like the Cartan matrix is negative definite or something like that?
Cartan matrix,
Yeah.
is it negative definite? No, it is not negative definite. In particular, the Cartan matrix of SU2 is 1 by 1, and it is a number 2, which is positive definite. For actually, so this this is the piece of representation theory that I will need. Yes?
How did you define mu alpha?
Mu alpha is an eigenvalue of H alpha acting on this state.
Okay, okay. So just the Dinkin label.
Yes. Any other questions? I suggest to make a 5-minute break before we proceed.
Okay,
All right.
let's start.
So let's continue. Let me give an example. So let's consider vector representation of SO6. So SO6 has has rank 3. And the Cartan matrix is usually represented by a Dinkin diagram. So each of the nodes corresponds to a diagonal element of the Dinkin diagram, and the diagonal elements are all equal to 2. And the links, so on the links we have, so the value of the links is equal to -1. So the Cartan matrix, therefore, has this structure. It's 2, -1, -1, 2, 0, -1, 0, -1, 2. So what are the Cartan generators in terms of the rotation matrices? Well, we can first introduce rotations in, so the simplest Cartan basis is made of rotations in 3 orthogonal planes, right? In 6-dimensional space can be decomposed into 3 2-dimensional subspaces. The rotations in each of them commute. So let's denote them by G1, G2, G3. So G1 would be in the vector representation, this would be a matrix 0, 1, -1, 0, and the rest are zeros. J2 is rotation in the I guess 3-4 plane, and J3 is rotation in the 5-6 plane. So if you think of vector components on which they act, we can again introduce y, z, wy, z bar, wy bar, which will be complex components of the vector. And if you write down their charges under Cartan generators, then okay, so the under complex, so complex coordinates just acquire a phase under rotations. So they are eigenvalues of the Cartan generators with eigenvalues +1 for the holomorphic components and -1 for anti-holomorphic. And each of them has an eigenvalue 1 with respect to its own rotation generator. But the Chevalier basis is not this G1, G2, G3. So the basis is actually, it's, let me see, it's a linear combination of these elementary rotations. So and then there are corresponding raising and lowering operators. And it is basically, knowing the quantum numbers in the form of the Cartan generators, it is easy to reconstruct how the lowering generators act on the members of the representation. So the highest weight is, we can declare it to be the Z state. So its Dynkin labels of the Z state are follow from its charges. So let's see. So for that, J1 is equal to 1, J2 is equal to 0, and J3 is equal to 0. So H1, therefore, is equal to 0, H2 is equal to 1, and H3 is also 0. So the Dynkin labels of the highest weight state are therefore 0, 1, 0. And so this is Z. And then we can act by lowering operators. Now, the action of the lowering operator on the weight vector is by subtracting the corresponding row of the Cartan matrix. And you see that the only element that would produce something meaningful is the middle row. So if we subtract it, we would get 1, -1, 0. So then we can act by acting with E2. And this will be equal to 1. So here we can recognize W. Indeed, W has weights which are equal to, so it has non-zero J2, and J2 appears in all three Cartan generators. So indeed, H1 is equal to 1, H2 is equal to -1, and H3 +1. So this is the Dynkin labels. These are the Dynkin labels of W. So from here, we cannot apply E2 again. What we'll get is 0 because we cannot lower -2 further. You can see that there are no states that have the right quantum numbers. So so the quantum numbers of any of these states is either made of plus or minus ones. So there also the game is that the action of lowering operators should preserve this property. So for Z, the only way to do so is to subtract the middle row. But on the W, we can either act by the first row, so E1 minus, and then what we get is -1, 0, right, and +1. And this is Y. Indeed, Y has quantum numbers -1, 0, and +1. Or we can act by E3 minus. Then what we'll get is 1, 0, -1, which is completely opposite to the quantum numbers of Y. So these are quantum numbers of Y bar. So on this, we can act by, the only way to proceed is to act by E3. then what we'll get is -1 +1 and again -1. And this is opposite to the quantum numbers of W, so this is W bar. But we can also apply E1 minus to Y bar, but it's easy to see that what we get is again W bar, so we don't get anything new. So and finally, the only way to operate by lowering operators on this is by acting with E2 minus again. So then we get -1, 0, 0, and this is Z bar. And it's not possible to go further. But we also recovered all the states of the vector representation. So there is 1, 2, 3, 4, 5, 6 basis vectors of the representation. So this is how the Chevalier basis works for SSX. And it suggests how to build the Magnum spectrum of the SSX spin chain. So are there any questions here? All right, so then let me proceed with constructing the Magnons. So what we can do is basically it's very similar to what we did for SU2. So we started with the ground state with all spins up, and then we flipped spins one by one on various sides of the spin chain, then propagating them with some momentum. So here we can also start with the ground state, which will be state where all sites are occupied by Z. And then act by lowering operators on it. So, or in other words, we can replace Z by some other letter. So from that point of view, it seems that there are 5 elementary magnons, right? So we used one state to build a vacuum. So excitations seem to come in 5 different flavors. On the other hand, the number of lowering operators that we can naturally write is equal to 3, right? Because they correspond to simple negative roots of the Lie algebra. So we can define lowering operator by a formula like that. Where this is the lowering operator acting on L's side. So here alpha runs from 1 to 3. So from that perspective, it seems that there are only 3 elementary magnons. But the right answer is actually 4. And the way it works is the following. So if you look at this diagram, you see that the only operator by which produces something interesting when acting on the vacuum is E2, right? Then we create W, and then it can be propagated along the spin chain. So on the next step, we can act by either E1 or E3. But these generators will only act on the side where we have flipped Z to W, right? So it can only change flavor of the existing magnon. Then we can apply E3 in the one again and make Y and Y bar from W, then make W bar by applying two creation operators of this type. And so W, Y, Y bar, and W bar will be the elementary magnons that can propagate on the spin chain. But if we want to create a Z bar, first of all, we need a site where Z is already flipped to W bar. But we also need to act by an operator, by the second creation operator. And that will, apart from creating Z bar from the W, it will also create a magnon somewhere else because it acts non-trivially on Z. So in this sense, Z bar is not a real excitation of the spin chain. It's not a magnon. It's rather a remnant. So for the most part, if we act by two applications of E2, we will get two W's and some other places of the spin chain. So in other words, we'll create a second magnon. And only in the place where we act by the creation operators in the same place of the spin chain, we would find Z bar. So Z bar, in a sense, is a bound state of two magnons. So in other words, there are four elementary excitations, but all excitations can be created by applying operators of this type to the spin chain. Generic state will be given by acting by this creation operator on the ground state. And then we will need to correct a little bit the wave function to take into account interaction between the magnons, right? Because when they clamp close to one another, they will start to interact. So there will be some S matrix that describes their scattering. Fortunately, we don't need to do all of that. There is a because the beta ansatz equations, they follow a very rigid structure related to group theory. So the only message that we need to take home from this picture of magnon creation operators is that they come in three flavors, and each of them can carry certain momentum. So in general, spin chain state will be then characterized by three sets of momenta, or we can parameterize them by three sets of rapidities. So U1, J, where J runs from 1 to K1, U2, J, and U3, J. So at the end, scattering of these magnons will result in some beta equations for these three sets of rapidities. And it appears that beta equations, due to integrability, they only depend on the underlying group structure, namely on the Cartan matrix of the Lie algebra and the Dynkin labels of the representations in which, or the representation in which the elementary spin living on white side transform. So let me write down this answer and then I'll explain what it means. So So these equations will describe the spectrum of the spin chain. And basically, the entries in these equations are, well, the rapidity themselves, but also the Dynkin labels of the representation and the elements of the Cartan matrix. And then the energy will be given by the formula that involves, well, the same data. So these are the beta equations that describe the spectrum of any spin chains that you can write with particular with a given symmetry group. So one simple check is that is to see that if you take the group of rank 1, which is SU2, then that you reproduce the beta equations for the Heisenberg model. So in that case, we need to set A to 2. So the Cartan matrix is not a matrix, it's just a number. And then the Dynkin label of the spin 1/2 representation is 1. And you get the beta equations of the Heisenberg model. For SO6, well, we just plug in the Cartan matrix of SO6 and the Dynkin labels of the vector representation. So the Cartan matrix is written here, and Q is so for the vector representation, the highest weight has Dynkin label 0, 1, 0. So this defines the beta equations for the spectrum of the spin chain. So it is interesting to notice that that the different nodes of the spin chain, they play different role in the beta equations. So if you set Q to 0, then the left-hand side becomes 1. And there is no contribution to energy because it's proportional to Q. So magnons that live on these two nodes, they do not carry energy and momentum and play completely auxiliary role. And this is reflected, this is a reflection of the structure of representation. So their role is to change the flavor of existing excitations, but they don't produce any new magnons. So the magnons corresponds, real physical magnons that carry energy correspond to this middle node. So people sometimes call this momentum carrying node, and these are auxiliary nodes of the Dynkin diagram. But all in all, this describes the solution for the spectrum of SO6 spin chain, and through that it describes the spectrum of all of the anomalous dimensions in superanomalies theory at one loop. So any questions? Yes, yes, of course. Well, they all belong to the same representation of SO6, right? So you can rotate Z to Y by SO6 transformation. So the vacuum forms a huge representation which has Dynkin labels 0, L, 0. And like for the Heisenberg model, the ground state is not just spin up, but all its SU2 partners. So if you can flip one spin with 0 momentum, that will be the ground state as well. So yes. So I forgot to add, by the way, that any solution to beta equations describe a highest weight state in a given representation. So all other states will have the same energy, but the multiplicity, of course, there is always non-trivial multiplicity. So for instance, the ground state forms a representation that has very large dimension, and it contains y state and w state and many other states. Any of them can be obtained by some particular SO6 rotation.
Thank you very much.
I wanted to, from here, to proceed directly to supersymmetric spin chain because so this describes only scalar operators, but we want to be able to find anomalous dimensions of, say, trace F mu squared or operators that contain fermions. Again, this can be neatly included using group theory, but maybe I should give an example of the use of these equations. So what do you prefer? Example would be good. Well, let me see if I can do it without preparation. But I hope that you will be able to help me out if something doesn't work. So let's try to compute the anomalous dimension of Kanishi from here. All right, so Kanishi operator is it's an SO6 singlet. It has length 2. And it's a singlet under SO6. So in principle, we can start with the state of length 2. So it will have quantum numbers 0 to 0. And we need to add some number of beta roots to make a singlet out of it. So if we add one beta root here, that wouldn't be enough, right? Or would it be? So what we'll get is, so adding one root here would subtract the middle node, the middle line of the Cartan matrix. All right, so what we'll get is 0, 1, 1. Then we can, so we don't get a singlet, right? It's a non-trivial representation. So we can try to mitigate it by adding roots here and here, but that would spoil this 0 in the middle. So what we'll get is minus let's see, minus 2, minus 1, 0. So that would produce minus 1, right? It's minus 1, minus 2, minus 1, plus 1, 1. Then we subtract 0, minus 1, 2. We get minus 1, 2, minus 1. So we need to subtract the middle node again, right? So with this constellation of roots, we will get a singlet. So therefore, we did a solution of beta equations with 2 roots here and an auxiliary root on each of the auxiliary, and 2 auxiliary roots on each of the external nodes of the Dynkin diagram. So we want a state that has 0 momentum. So it should be symmetric under, well, I mean, one way to achieve it is to have these 2 magnons opposite momenta and put these roots at 0. So we have 1 root at 0 on this node, and on this node we should have 2 roots, and the root at 0 here. So then we need to write 3 sets, actually 4 sets of beta equations for each root. Of course, by symmetry, we don't need to check the equation for root minus u. But yes, so we need to write down the equations for this root, for u, and for root on the other auxiliary node. So on the auxiliary node, the equation will be 1 equal to 0 minus u minus I over 2 divided by 0 minus u plus I over 2. And then there will be an interaction with the other root, which will be plus u minus I over 2, 0 minus u plus I over 2. So altogether, wait a minute. Something. Yes, there is a plus here. And I guess this is equal to 1, right? So this equality is satisfied. Because this cancels with that up to a plus up to a sign. And this cancels with that also up to a sign. So in total, I have 1. So this equation, the auxiliary equations work, irrespectively of what u is. And then we need an equation for u, so we write the middle node equation plus I over 2, u minus I over 2, raised to the power 2, and that should be equal to well, there are quite a few terms here, so it will be 2u minus I, sorry, 2u plus I, 2u minus I. This is an interaction between the roots on the middle node. But then there are also 2 auxiliary roots. So this will produce u minus 0 minus I over 2, u minus 0 minus I over 2 plus I over 2 squared, because there are 2 auxiliary roots. So at the end, things simplify because all of these factors is just u over u plus I over 2 divided by minus u over 2. And in total, what I get is this equation. I think. So because, this is u plus I over 2 divided by u minus I over 2. And this is the inverse of that, but this is squared. So I bring it on the left-hand side, I get this equation. The solution to that we already found today when we discussed the length 4 state in the Heisenberg model. And from there we found that the value of the root, I believe, is square root of 3. It's probably, yeah, let me just solve this equation explicitly. I can write it as u plus I over 2 cubed equals to complex conjugate. Yes? I think it's canceled, so they cancel between them. Okay, so then I have this equation. And this equation tells me that the imaginary part of the left-hand side should be 0, right? So this should be equal to its complex conjugate. Yeah, so the imaginary, so it should be a real number. So let's compute the imaginary part of this, and this will be I over 2 times 3 times u squared plus 3 I over 2 squared. Just a second. It's I need I need to use binomial formula, right? So this is 3 times. No, this is not the right thing. So then I should pick up the last term, which is I over 2 cubed, right? And that should be equal to 0. So this is equivalent to 3u squared minus 1/4 equal to 0. So u squared is equal to 1/12. So now I plug it in the solution for the energy. So the anomalous dimension differs from the energy by a factor of lambda over 8 pi squared. There are 2 beta roots. Each contributes u squared plus 1/4 to the energy. I replace this by 1/12. So this will be lambda over 4 pi squared times 4 times 12 divided by 3 plus 1. So this is 3 lambda over 4 pi squared. I guess I passed my exam in linear algebra. So it works. So this is basically how the beta ansatz work. You reduce everything to algebraic equations. And for Kanishi, of course, it's probably easier to compute it from Feynman diagrams. But if you consider some huge state that contains a lot of fields, then beta ansatz becomes more and more effective. And yes? Yes. So why they're set to 0? So we want a state that has 0 momentum. So it should be invariant under rotations of the spin chain by under translations. But then for a spin chain of length 2, translation is the same as reflection. So so we want a state that is invariant under reflection that inverts all beta roots. So reflection acts on beta roots is by inverting them, because they're basically, they parameterize momenta in some way. So one way to achieve this is to place, so that there are 2 ways to achieve it. Either we place beta roots in symmetric points or at 0. So we know that on the outer roots, on the outer nodes, there is only 1 root. So there is no way to compensate. If you put it somewhere else, there is no other root that can compensate for this parity violation. So the only way to put it in a parity invariant way is to set it to 0. So so now we want to generalize this to all operators, and you may guess how to proceed. We just need to consider a bigger algebra. So the equations will still be of this form, because beta equations happen to always be of this form for the spin chains that have enough symmetries. So we need to understand what should be the entries here. What is the Cartan matrix, and what are the Dynkin labels of the representation of that we use in the spin chain. And this data, of course, is very easy to read off from field theory. So in field theory, we basically on each side we can put either scalar fields or their derivatives. Or we can put gauge fields, fermions, etc. So all of these fields can be put into a single representation of the superconformal algebra. So basically, we need to understand what is the Cartan matrix of the superalgebra of extended supersymmetry, and that would immediately produce the beta equations that we need. Yes.
Could you summarize it? What exact situations are beta equations the right solution? Like we began for SU2 and we derived them somewhat, and then we extended them to so many arbitrarily to SU6.
Yes. So the logic here is the following. Once you have, integrable spin chains, there are very few of them. So there is only one integrable spin chain with the SO6 symmetry. It's just a piece of knowledge that the beta ansatz for a spin chain with such and such group structure has this form. So on the other hand, by direct computation from field theory, we observed that the mixing matrix has an SO6 symmetry, and it is integrable, so its solution beta B of this form. So it's essentially bootstrap logic that we know how the answer should look, provided that the system is integrable. Then we check that indeed what we got is an integrable Hamiltonian, and then we don't need to go through the algebra of deriving beta ansatz because we know that the endpoint will be these equations.
So somehow we should be able to say something like if the Hamiltonian has this and this symmetry, beta ansatz would be the solution, right?
Yes, provided it is, yes, precisely.
Yeah.
Provided it's integrable.
Provided it's integrable. And that condition means what part of our calculation we checked? If just because we had those extra, some supercharged Q, we didn't check
So
that.
for SO6, this was sort of checked if you believe me that this operator Q, that X on three sides commutes with the Hamiltonian. For this general spin chain, I'm not sure it's ever been done, but well, there are, reasons to believe that the system is integrable. Particular string theory tells us that that there is an underlying integrability. So if you believe that the system is integral, you can write down the beta ansatz equations. But then beta ansatz produces a lot of spectral data, and that can be checked against explicit calculations. So this is how one can proceed.
Okay.
So indeed the power of integrability is in its rigidity. There is not so much you can write in terms of equations. So once you know what the symmetries are, basically that fixes the answer. That fixes the answer. So in that sense, the answer can be that you can achieve your goal of finding the spectrum basically without doing explicit calculations. Well, I guess I would need to stop in 5 minutes. Maybe I'll just finish here. And tomorrow I will talk about superconformal symmetry and write down the full answer at one loop, and then maybe say a few words how it is extended to the old loop answer without much detail, because there are some technical steps that would take longer to explain. Thank you very much.
Questions? Nobody? Well, you have half an hour to think of some more questions until the questions and answers session. So let's go to coffee break now. Oh, sorry, there's something. Given a theory, how could one tell if it has an underlying integrable structure?
How can one tell? So one can explicitly construct hard charges, or well, look in the books and see if it's already there. But there is an algebraic framework that allows one to build integrable Hamiltonians. It's called algebraic beta ansatz, and so, as far as I know, all integrable systems possess this deeper integrable structure. So, and it is also based on symmetry. So there's basically a single R matrix for any symmetry group. So you can construct the Hamiltonian from this data, and it's basically unique. So indeed, if you're lucky, you probably would find something that's already known. Yes.
Oh.
But it's not that all the integrable systems are already classified or something.
I would say yes, under certain assumptions, yes. So, for instance, if you say that spin chains that are symmetric under given Lie algebra, so if you insist that this Hamiltonian is invariant under E8, then there will be a unique Hamiltonian that's integrable and is known. So maybe there are some obscure integrable systems that do not have enough symmetries, or are very non-local, that are not classified. But actually, AdS-CFT integrable system that underlies AdS-CFT was not known. It was something new that was constructed specifically for the purpose. The reason being that at higher loops, the Hamiltonian is no longer local. And so once you give up on locality, then many things can happen.
All right, so let's thank Konstantin and come back in half an hour.